Hello once again. Let's go over the review sheet for Unit 4 from Physics in the fall. And this wasn't so bad. I can't remember if you guys did really well on the test or not, but there are not as many topics as for Unit 3. So basically, this is energy and plugging numbers into equations to find out certain energies, conservation of energy, which might be the little trickier part we'll get to, a little bit about power at the end, and then at the beginning here, a little bit about periodic motion. So not so bad, but just make sure you have all the equations written down. So let's start with the questions on periodic motion. A pendulum moves to the right and back to the left 20 times in 50 seconds. So what I'm describing is, let me get my pen, is here's the pendulum here, and it goes to the right and back to the left 20 times in 50 seconds. So how many cycles did it complete? Well, the cycle is just that, going to one side and coming back to where it started. So that 20 times is referring to 20 cycles. Now, what's the period? Well, it's not really an equation for this. It's just by the definition of period. The period is how long it takes to complete one cycle. What's the time per cycle? So it took 50 seconds to do 20 cycles. So it takes 2.5 seconds per cycle. However, typically for period, it's implied that it is per cycle. So we typically just don't include cycle. We just say 2.5 seconds. You can, there's no problem with that, but you'll just more often see it just written as a time unit. Now, what's the frequency? Well, the frequency is how many cycles it completes per time, per second, per minute, or whatever. So it completed 20 cycles per 50 seconds. And so that you get 0.4 cycles per second. And here you typically will leave it cycles per second. You won't cross out the cycles. Although you will see some people just writing it 1/seconds or seconds to the -1. But we have another way of writing that as well. Remember that also represents hertz. Now, there's another way to get the answer for frequency, which is I'm going to use this in number 2, so I'm not going to redo it. But remember that the frequency and the period are reciprocally related. So if I knew that the period was 2.5 seconds, I just take the reciprocal of that, and that's the frequency. All right, so remember that, how to get those things. There'll probably be one question about frequency and period there. Let's say that in that time, the pendulum moved a total distance of 240 centimeters. What is the amplitude? Okay, here's something I told you to memorize. Well, first of all, identifying something here. Let me just use another color. Let me split this down the middle. The amplitude is the maximum displacement from the average or resting position. So that represents the amplitude from where it would be resting if it weren't vibrating back and forth to its maximum displacement to the left or the right. So in one cycle, when the pendulum goes from there and back to there, how many amplitudes does it complete? It completes 4 amplitudes per cycle. That's just a useful thing to know even for wave motion, like the medium is going to move 4 amplitudes per cycle. All right, to get back to the problem, we said that it did 20 cycles. So how many amplitudes will the pendulum move in 20 cycles? Not rocket science here. It'll move 80 amplitudes. Now, 80 amplitudes is represented by 240 centimeters. I'm not sure if that's the right word to use there, but it moved 240 centimeters, which is 80 amplitudes. So how big is each amplitude? Each amplitude is 3 centimeters. So not an easy problem by any means, even though I'm sure it was easy at the time that you were learning that. But just remember that there are 4 amplitudes per cycle, and then logically figure out whatever I'm asking you. I could kind of mix that problem up many ways. All right, let's get to number 2. The period of a guitar string is 1/500th of a second, 0.002 seconds. What is the frequency? And that's where this equation will become nice and handy. The frequency is 1/period, or the period is 1/frequency. They're just reciprocals of each other. So all we need to do is take 1 and divide by the period, and you get 500. And then here you see it's just going to be 1/seconds, You could leave it 1/seconds as the frequency, but usually we just slap on a cycle because it's a good way of thinking about frequency. It's how many cycles per second, or you can write it as hertz. Okay, so don't forget to write that equation on your note sheet, how we get from frequency to period, back and forth. Number 3, the period of a pendulum is 2 seconds. I double the amplitude and triple the mass. What will be the period? So maybe I'll ask this again. Again, I said this a few times over these review sheets. I'm not trying to be coy. I don't want to give away too much, but also I'm just not sure if I'm asking this on the final. I'll probably edit the final a little bit also, so I can't guarantee it. But this goes back to the topic of, we did this lab where we saw what affected the period or frequency of a pendulum. So what affected it? Did amplitude affect it? So if you pulled it back a little bit farther, did it affect it? Actually, no. You might think it did, but it didn't. I won't go into the explanation because I'm not going to ask you that on the final. Did the mass affect it? No, the mass did not affect it. So if I change the amplitude or the mass, the period and the frequency are not going to change, so it's still 2 seconds. Now, the one thing that did affect the period or frequency of a pendulum is the length. So if I double the length of the string, what's going to happen to the period? Well, it will change. But think about it. Can you remember what happened? Like, visualize like having a really tiny string and it vibrating back and forth, and having a really long string and vibrating. Which one was slower? The long string, right? So if I'm doubling the length of the string, imagine now that pendulum going back very slowly. So the period, how long it takes to complete a cycle, will be longer. If I asked you the frequency would be shorter. It'd be small, I should say shorter, but better adjective is to be, the frequency would be lower. This is kind of good because there could be and probably will be one, possibly two, but I might not waste 2 questions on this, but one question somewhere about just purely about units. Do you know what each thing represents? I can't say it's necessarily going to be joules, but it could be newtons, it could be watts or whatever. So make sure you know what each one of those kind of abbreviations for a unit represents. So the simplified units of work and energy are joules and foot-pounds. Those are the SI and imperial units. Write the joule 2 other ways and the foot-pound 1 other way. So a joule is equivalent to a newton times a meter, newton meter. But it's also more simply, because a newton is a kilogram meter per second squared, a joule is a kilogram times meter squared over a second squared. And a foot-pound, there's no kind of smaller abbreviation for the imperial energy or work there. It's just foot-pound. But if you remember that a pound is a slug foot per second squared, this is going to be a slug foot squared per second squared. So write those down somewhere. So if I ask you something like that, you'll be ready. Or if I also write down what a watt is or things like that, or a newton or a pound. Number 5, true, false. An object has 200 joules of kinetic energy. You do work on it so that it ends up with 150 joules of KE. That means you did 50 joules of work. So let me pause for a second. I'll erase this. I'll just put it down here. We'll get to these in these problems we're about to do. But work has 2 different ways we can write an equation for it. And going back to the previous unit, we did impulse. Impulse changed the momentum. So we said impulse, I'll just write it here, was the change in momentum. But impulse was the force that you exert times the time you exert it. So there were 2 ways of thinking about impulse. Well, the same thing about work. Work, we can think about it in 2 ways. Work changes what? It changes the energy. And some people will write change in kinetic energy. I don't want to get into all that, what that means, but I just think about it as change in energy. Or we could say that work is equal to the force that you exert times the distance. So be flexible, depending on what's asking in the problem. Know that work is either just changing the energy, or it's the force that you exert times the distance. Okay, so keep those in mind as we answer these next questions. So back to number 5, it says, an object with 200 joules of KE has 200 joules of KE. So we're doing work. We're changing its energy, and I guess we're just changing its KE. It ends up with 150 joules of KE. So did we do 50 joules of work? Well, it sounds like it, but you probably know the answer is false, because why? You did negative 50 joules of work. Work is not a vector. There's a question later on this review sheet about that. Negative doesn't mean a direction. It just means you're doing work that lowers the energy of the object. So positive work increases the energy of the object. Negative work decreases the energy of the object. So since the Ke dropped by 50 joules, we must have done negative 50 joules of work. 6, a block is already moving to the right on a flat frictionless surface with 70 joules of Ke. I just kind of bring that up as flat and frictionless, so we're not worried about heat being created or having GPE created. So it's all about Ke here. We just have something gliding along on a frictionless surface, not increasing in height. You push against it to the left. It's moving to the right, so we're pushing it to the left with a force of 100 newtons for a half a meter. How much Ke will the block now have? So, first of all, are we going to be doing positive work or negative work on this? Negative work, right? Because we're pushing in the opposite direction, we're going to lower its Ke. So we're going to expect something lower than 70 joules for our answer because we're pushing against its current motion, doing negative work. All right, so we give you the force and the distance. So as I said, be flexible. The work is the force times the distance. And I'll go ahead and be technical here. If it's moving to the right, I'm saying that's the positive direction, I'll say the force I'm exerting is negative 100 newtons, just so we can get because we know we're doing negative work. Sometimes you just throw it in there just to have the negative. And then we push for 0.5 meters. And if I'm using newtons, I want to use meters. So if I tried to trick you, which I won't on the final, and gave you that I pushed with 100 newtons for 0.5 feet or something, you'd have had to convert feet to meters so we can get our nice friendly joules as our units. So we did negative 50 newton meters or joules of work. So now let's get the answer. If it has 70 joules of Ke and I do negative 50 joules of work, how much Ke will it have at the end? 20 joules or 20 newton meters. Not too hard, right? It's just that you haven't done these in a while. So again, be patient, study, and these questions will be kind of straightforward if you just remember work equals force times distance and work equals the change in energy. Number 7, you want to change the Ke of a cart. So these next two are very similar to what I just did. You want to change the Ke of a cart from 80 joules to 170 joules. If you push for a distance of 3 meters, what force do you need to exert? Well, notice that we change the energy. And just assume, if I'm not telling you any other energies, all the energy is going into, all the work is going into changing the Ke in this case. So remember, the work is the change in energy. So it changed by how much? 90 joules. Right? We did 90 joules of work on this. So now we're asking, how much force do I need to exert if I could only push it for 3 meters? Well, now we use the other equation, that work equals force times distance. And we know the force times distance, the work is 90 joules. So I give you the distance of 3 meters. So in other words, the force is going to be 90 joules. I'll just write it this way, Newton meters, so we can see it canceling. That's what a joule is. Divided by the distance, which is 3 meters. And therefore you can see the meters cancel. And what's the force you exerted? 30 newtons. Again, not really that hard. Just practice and you'll be fine. Number 8, a 30 kilogram shopping cart is rolling towards you at 4 meters per second. You push on it in the opposite direction with a force of 400 newtons. What distance is required to stop the cart? So to stop the cart, we want it to have what Ke at the end? 0, right? So we need to figure out what Ke it has initially, and then we could figure out what the change in energy is required in order to bring it to a stop. So let's first find the Ke. We haven't done that yet. I haven't used that formula yet. So of course you'll have this written down. You probably memorize that one, but write it down anyways. So sorry, my palm shouldn't keep doing that, but it is. 1/2 times 30 kilograms times the initial velocity is 4 meters per second, and we're squaring that. And remember, we're only squaring the 4. So 4 squared is 16 times 1/2 is 8 times 30 is 240. Kilogram, I'll write it this way so you remember, kilogram meter squared per second squared, because we squared the meters per second, which is just more simply 240 joules. So back to what I was saying, the cart is starting with 240 joules, and I want to stop it. So how much work do I need to do on it? I need to do negative 240 joules of work because I need to get rid of all that kinetic energy. Now again, work really isn't a vector. It's just saying negative just means you're going to do something that lowers the energy of the object. Now what does work also equal to? Write this down in your little cheat sheet. It's equal to force times distance. So it's similar to number 7, we're just solving for something else. So our force times distance must equal negative 240 joules. So in other words, the distance required is negative 240. I'll go ahead and put Newton meters here again so we can see it canceling, times the force, which again, the distance, if you put in positive, because I wrote 400 newtons in the problem, you would get a negative distance. Who cares? I'm just looking for a scalar, a distance. So you just drop the negative. But technically, if I was saying the velocity is positive 4, but I'm pushing in the opposite direction, the force I actually exerted was negative 400 newtons. So now the newtons cancel. And negative 240 over negative 400 actually turns out to be 0.6 meters. Okay, how's that going? All right, an easier problem here. But still know these, I'm guessing there might be one question on the physics half of the final where I ask you about vectors versus scalars. So again, vectors are quantities that have a spatial direction associated with them. Scalars have no spatial direction associated with them. So which of these are vectors? Force, you should know that, and velocity. GPE, KE, all energies are scalars. Remember that, write it down. Again, I don't know if I'm going to ask that, but just for safety's sake, write down that all energies are scalars. Also, work is a scalar, okay? But that doesn't mean some quantities that are scalars can't be negative. So the second part, circle all the things that could be negative. Well, we'll get to the vectors. Of course, vectors can be negative. That's just direction. KE cannot be negative because remember, it's 1/2 mv squared. And so if there was like a direction, like, in a negative direction, squaring it kind of gets rid of the negative. But GPE can be negative because negative GPE just means the object is lower than whatever you said was your 0 of GPE. So if I'm calling my table here, my 0 of GPE, if something's on the floor, it has to have less GPE, so it would have negative GPE. It's not a vector, it's just saying it has less GPE than whatever you're calling your 0. And work can be negative, again, not that it's a vector, it just means that negative work, hey, you're doing something that's lowering the energy of the object. All right, number 10. What is the GPE relative to the ground of a 200 gram, ooh, that should look ugly. What do we always use for masses? Kilograms, right? Book that is on a table, 90 centimeters. When do we use centimeters? From the ground. So we're gonna have to do a couple of conversions. We'll just do them in our head. Make sure to use the correct units to get joules. So another formula I'm sure you'll write down, you won't forget, is the gravitational potential energy is the mass of the object times the acceleration due to gravity on that planet times the height from whatever you're calling your 0. So we're saying the ground is 0, and I gave you the height from the ground. So we're gonna plug in the mass, and no, we don't use grams. Oh, you could, you wouldn't be getting joules here. So let's try to keep it always doing SI units. So we're gonna change 200 grams to 0.2 kilograms. There are 1,000 grams in a kilogram. Write those down if you don't know them. G, let's just still keep using 10. And H, we wanna use meters, but there are not 1,000 centimeters in a meter, there are 100. So that's actually 0.9 meters, not 0.09 meters. And when you plug those in, I just don't have my calculator, so I'm gonna look at my answer key here. Where is it? There it is. 1.8 kilograms meters squared per second squared if you looked at all the units multiplied by each other. But again, that's just a joule, which is just easier to write, right? All right, let's get to number 11. So that's what I said at the beginning of this video. A lot of it is just hey, finding that equation and plugging things in. Yes, it'll get a little trickier later. And yeah, these work problems were a little tricky, but mostly it's going to be a lot of equations plugging in. So you guys can do this. You're smart. What's the KE of that 200-gram book if thrown at 12 meters per second? So let's practice using the KE equation again. So KE equals 1/2 mv squared. That's 1/2 mass. We're going to use what if we want joules? I didn't say you had to. So it's technically, if you answered in something like grams meters squared per second squared and you had the right number, sure. But the multiple choice, I'm going to be giving you the 5 possible answers in joules. So make sure you're using kilograms when you're doing mass. So 0.2 kilograms times velocity, 12 meters per second squared. Again, we're only squaring the velocity. So when you do that, again, I'll just look at the answer key. Where is it? Number 11. You get 14.4 kilograms meters squared per second squared. But again, I'll just quickly write joules. And again, why? Because you're squaring not just the 12, you're squaring the m and the s. So you get kilograms meters squared per second squared, which is, again, the same thing as a joule. All right, some more where we're just plugging things into an equation. I hope you guys are saying, yes, give us a lot of those. So we're going to do another KE problem, but this time we're not solving for the KE. We're going to solve for, what are we solving for here? M, the mass. So back to 1/2 mv squared. Now here's a pro tip. If you're not good at algebra, and some of you aren't great yet, you're going to be great at it soon, but I see a lot of mistakes where you can't solve this for m or v or whatever. If that's you, then write down on your little cheat sheet every variation of this problem correctly solved. So for example, you'll hopefully have written that the mass is 2ke over v squared. And that way you don't have, not only are you not going to make a mistake as long as you wrote it down right, but if it takes you maybe 20 seconds to realize how to solve that, which for some of you it might, here's 20 seconds saved because you're going to have a different equation solved for m, or that same equation solved for m. So anyways, using the correct equation, we're going to do 2 times 36 foot-pounds, which is an imperial unit. So velocity, we want 30 feet per second squared. 30 feet per second squared, not 30 feet per second squared. This is not an acceleration. So 30 feet per second squared. Now, how do the units work out? It looks kind of weird how we're going to do that. But remember that a foot-pound is the same thing as a slug foot squared per second squared. So when I square the foot per second, I get foot squared per second squared, right? So that's actually going to cancel that. And what are we left with as our unit? A slug, which is what we want for the mass if we're using imperial units everywhere. So when you plug that in, you supposedly get, as long as I didn't make a mistake on my answer key, 0.08 slugs. And I could probably on a problem try to trick you by maybe choices A and B, writing something like 0.08 kilograms on that. And then you'll see 0.08 and you'll go, oh, there's the answer, and you'll circle it. So pay attention to your units and don't be tricked. 13, yet another one. We're going to do a couple more where we're just using equations. But back to GPE here. In fact, we haven't used, somewhere we did. I thought we used a GPE formula. Yeah, up there. So we're going to use GPE again. A 2.4 kilogram rock is on another planet and has 42 joules of gravitational potential energy at a height of 3.5 meters. What is the acceleration due to gravity on that planet? So let's go ahead and solve this. And just like I said before, even though this is a much easier one to solve, if you're a little worried that you're going to get this upside down or something, write every variation of this correctly solved for it. So we're looking for little g, and that's going to be the GPE over mh. So we plug in the GPE, which we're back to SI. MH. Did I just erase it? I thought I had it there. Maybe I did an undo button. And then the mass is, where is it? 2.4 kilograms. And the H is 3.5 meters. And I won't go through the whole cancellation of units, but again, what I'm saying is you have the right formula, you're using SI units everywhere, you're going to get the appropriate SI unit for that problem. So numerically, you're going to get 5. And what should be the unit if we're solving for an acceleration due to gravity? meters per second squared using SI units. So again, you could rewrite joule and then see what cancels, but it is meters per second squared. All right, what is the weight of that rock on that planet? Just to practice the skill again, I'm sure there's going to be somewhere or a couple places where you're going to have to know how to find the weight. So the weight, which we're using F sub g to represent, is just the mass of the object times the acceleration due to gravity on that planet. So let's don't go back and throw a 10 there, because we just found out that the acceleration due to gravity is not 10 there, it's 5. So we're going to put in, darn, keeps doing that. Sorry about that. It's supposed to have this palm rejection. When I put my palm down, it's supposed to ignore it, but it keeps moving. So mass is 2.4 kilograms, and the acceleration due to gravity on that planet is 5 meters per second squared. So that's going to be 12 kgm per s squared, or newtons, which we kind of expected for a weight in SI units. Okay, here's something that, I'm going to probably have something on the final that has SPE. I won't do anything with the spring force. We learned that this was the equation for the spring force. But when we get to, as you'll see later on this review sheet, conservation of energy, there might be on the final something using the equation for SPE. It's 1/2 times the spring constant, K, and that just depends on the spring. I would give you that value as long as you're not solving for K. I would just give you that. It's going to be some force per distance. And then times the displacement, how far you have squeezed or stretched the spring, that's delta X squared. So I didn't have that on that summary sheet for the final information. So I'm going to try to tell you guys many times, include this equation on that. I'll just go ahead and skip asking you that on the final. But you might need this. So write it down on your review sheets, or not review sheet, your cheat sheet. Okay, let's get to the problem. If the spring constant is 100 newtons per meter, that's all right, what force does it exert when you stretch it 20 centimeters? So the force exerted by a spring, or that you exert to squeeze or stretch the spring by a certain distance, is just negative, because it's always a restorative force. If you're squeezing, it's pushing out. If you're pulling, it's pulling back in, right? So it's just opposite whichever direction you're stretching it. Don't worry too much about it. I always just kind of think of it as, what's the magnitude of the force? So it's just the K, which is 100 newtons per meter for this spring, times how much you've displaced it, not squared, but just how much you displaced it. But we have meters here, so let's change our 20 centimeters to 0.2 meters. So that's going to be 20 or negative 20 newtons. Like I said, I just think, okay, what's the force? 20 newtons. It's kind of weird to think about which direction, because you might be squeezing from both sides, right? So that'd be negative 20 newtons. Again, I won't ask that on the final. But let's solve for the SPE. That might be useful. So the spring potential energy, some people just call it the elastic potential energy, is going to be just 1/2 the spring constant times the displacement squared. So it's 1/2 times 100 newtons per meter. That's the spring constant. And then again, it's 0.2 meters is how much you've stretched it, squared. And just going, that's going to be 0.04, right? Times 100 is 4, divided by 2 is 2. And the meters cancel. I'm sorry, they don't cancel. We got meters squared here, right? That'll cancel this meter, or one of the meters will cancel that meter, you know what I mean? And we end up with Newton meters or joules. But just from the units I have there, you'd get Newton meters, but that's the same thing as a joule. So do know that equation for the SPE. Number 15, if you double the height of an object, what does that do to its GPE? So you're holding that object at some, like say 1 meter from the ground, and now you're going to lift it so it's 2 meters from the ground. How much bigger is the GPE? Well, it's going to be twice as big, because the GPE, I'm sorry, not that one, depends on the height, but linearly on the height. If you double h, you're going to double GPE. If you triple h, you triple the GPE. But let's do something with KE. Notice that KE depends on velocity squared. So if I change the velocity of the object, I'm going to change the KE by the square of how I change the velocity. So if I double the velocity, if I double V, well, notice I'm squaring that. So it's kind of weird to say. It's like if I square the doubling, what effect does it have on the KE? It's going to be 4 times bigger. What if I said you tripled the velocity? How much bigger would the KE be? 9 times bigger. What if I make the velocity 5 times bigger? The KE will be 25 times bigger. So whatever you do to the velocity, the KE changes by the square of that factor that you change the velocity. I guess that's a good way to say it. All right, let's keep going. I'll try to do the whole worksheet in one video here. So I'll speed up a little bit. Imagine a car going 5 meters per second. And this problem is related to what I just did in 15. Imagine a car going 5 meters per second down the road. That's not very fast. The brakes are slammed on and the car skids to a stop in 20 meters, just in time to avoid a crash. Now imagine the car goes twice as fast. So it's going 10 meters per second to the 5. How many times more KE does the car have now? So if we doubled V, remember that KE depends on V squared. So if we're doubling the V, the KE will be 2 times bigger, right? Twice. I'm sorry. I was concentrating on something else and I wasn't thinking. Yeah, we double the KE, so the KE will be 4 times bigger. How many times more work must be done to stop the twice as fast car? So the work, remember, changes the energy. And in this case, we're just changing the KE. So if by doubling your velocity, you have 4 times as much KE, you now need to do 4 times as much work, or the brakes need to do 4 times as much work to stop the car. So if the car, part C, has the same braking force, F, what will happen to the stopping distance when the car is going twice as fast? So the work, remember, is also the force times the distance. So if our work is 4 times bigger by going twice as fast, our F times D is going to be 4 times bigger. So if the brakes apply the same F, whether we're going 10 meters per second or 20 meters per second or 5 meters per second, then that means D has to be 4 times bigger, 4 times farther. And that's what I'm saying right here is that, yeah, when you go a little bit faster, because the kinetic energy, and therefore the kinetic energy is going to be changed by the square of however much you increase your speed, the work is going to be increased by that bigger factor. So the brakes will have to be exerted for that same fact. I butchered that explanation. I'm moving on. Okay, I think you know what I mean. All right, here's some problems that people struggled with a bit. I was surprised that people struggle with these. So I'm going to do like a little bit of a review here that might help you and talk about what is indicative of changes in these types of energies that I'm going to be bringing up. So GPE is all about height. Well, yes, of course, it depends on the acceleration due to gravity and the mass, but assume that we're talking about the same object, so we're not changing its mass, and we're still on the same planet, we're on Earth. GPE is then all about how high it is from the ground. So GPE, what we're looking for is a change in height. What I mean by this is that's what we're looking for a change in GPE. We're looking for a change in height. So if we make the object higher from the ground, we've increased the GPE. If we bring it closer to the ground, we've decreased the GPE. Okay. What about KE? KE is 1/2 mv squared. So assuming that we're not changing the mass of that object, it's all about changing the velocity. So that's what we're looking for to identify that the KE is changing. We're changing the velocity. What about next on the list up there at number 17 is Q. Q represents the heat generated due to friction or collisions between 2 objects. So we know that heat is going to be created if you have like a collision or some kind of friction, something sliding relative to another. We don't decrease heat. So you'll never say Q is decreasing. If anything, we're just making heat. So if there's some process where there's friction, there's air resistance, there's a collision, we're going to probably be creating heat. And now, of course, there are some, we can talk about collisions that don't create heat, elastic collisions, but that's generally what we're looking for. If there is no friction or no air resistance, none of these things, then Q could remain constant. But again, don't ever say Q is decreasing. It's either going to be constant or it's going to be increasing. And for SPE, assuming we're talking about the same spring or rubber band or whatever, the spring constant K is not changing. So what we're looking for is either stretching something that's stretchable or compressing something that's compressible that would spring back into shape. So that's what we're looking for to identify whether some kind of energy is changing and if it's getting bigger or smaller. Okay, so that's my little re-explanation of these things. So these hopefully will become easy then. A ball moving downwards runs into a spring, okay, it tells us something, and compresses the spring. Which forms of energy increase? Well, the ball is going down as it's compressing the spring. That's what I meant, is that it's still kind of heading downwards, actively compressing the spring. So is GPE increasing? No, as we'll soon see, it's decreasing because it's still moving downwards. How about KE? Well, if it's running into the spring, what do you think is happening to its velocity, its speed? It's probably slowing down. So that's going to be another one we're going to answer right below. How about heat? Yeah, we're going to assume, I didn't really say this, so I'll try to be clearer on this is just a review sheet. We're assuming that there's probably some heat created when the ball slams into the spring, but also if it's not a perfect ideal spring, the spring being compressed is going to generate heat. That's why if you have a spring and it bounces back and forth, sooner or later it comes to a stop because all the friction is going to create some heat. So yes, we'll be creating some heat when we are compressing that spring. What about SPE? Yes, we had an uncompressed spring, but as the ball is compressing it, we are, in the case, compressing it, so we're increasing the SPE. It's only when the spring is relaxing back to its normal length that it would be decreasing its SPE. Okay, so we kind of already answered the second part. Yes, GPE is decreasing because it is moving downwards as it's compressing the spring. It's getting closer to the ground. KE is decreasing because we're slowing the ball down. We'll never say heat is decreasing. And the SPE is not decreasing. In fact, we're increasing it by compressing the spring. Hopefully, that now in retrospect seems kind of obvious to you. Here's kind of a tricky one. I think this is going to cover one of my trick questions here, or maybe not, we'll see. A student runs up some steps at constant velocity. Which form or forms of energy increase? Well, if he or she is running up the steps, they're getting farther away from the ground, so GPE must be increasing, right? How about KE? Constant velocity. So if your V is not changing, can your KE equals 1/2 mv squared change? No. I think for some reason people want to say that somehow kinetic energy adds up, that you're running, and if you keep running, you're making more kinetic energy or something like that. So, they keep running, so they're making more KE. No, KE is just 1/2 times your mass times currently how fast you're moving. So if he's running up the steps at a constant velocity, his KE is constant. How about heat? I'm going to say yes, because in the real world, when you slam running up steps, you're creating little collisions with the ground. You're creating some heat. And there's nothing that the problem kind of specifies that you're creating SPE, unless you're saying something like you have very springy shoes or something, but we're not going to worry about that. Which form or forms of energy decrease? Well, I can't say those two, right? Because we just identified those as increasing. Not KE, because the velocity is constant. And there's nothing about SPE in the problem. Oh, wait a minute. This was that tricky thing I was talking about is I would always get somebody to answer one of those when they shouldn't, because they think of conservation of energy and they think, wait a minute, there are a couple of energies that are increasing. So by conservation of energy, there has to be some energy that's decreasing. And they kind of feel desperate and they say, well, I better circle something. I'll circle heat or whatever, KE or something. Well, it's not that I had to necessarily indicate every type of energy that could be changing. I just listed 4 possible energies. So think about it. What kind of energy, even though we didn't talk about it much this year, is decreasing as you're running up the steps, getting tired, You're burning calories, right? So the energy stored in your body as chemical potential energy is decreasing. You're using up some of your stored energy in your body. So yeah, that stored energy in your body is going into making that GPE, to make that heat. It's just that I didn't put that as an option. Okay, let's move on. 19, here's, I guess, another SPE problem. Let's say a ball rolls, oh, we're getting to conservation of energy here. So I'll just do this when I'll get to mechanical energy for number 20. Let's say a ball rolls with 4 joules of kinetic energy towards a spring that has a spring constant of that. It compresses the spring until the ball comes to a momentary stop before it springs back the other direction. If all the KE turned into SPE, so we're going to assume no heat was created here. So we're just having conservation of mechanical energy, as I'll talk about in number 20. How far will the spring be compressed? In other words, we're looking for delta X. Kind of a neat problem. So if we knew, for example, the mass and the velocity of the ball, we can figure out its KE, and we could figure out and anticipate how much the spring would be compressed when it runs into the spring, if you knew the spring constant of the spring. Okay, so just kind of a simple conservation of energy problem. I'm not going to do a whole equation here. If it has 4 joules of KE to begin with, and it's turning all into SPE, how much SPE does the ball have when the spring is most compressed and the velocity is 0, when the KE is 0? Because that's what's happening to the KE when it is most compressed and it's temporarily stopped before it springs back out. The KE is 0. Well, you've already answered it probably, is that the SPE must be 4 joules at that point. Now we have an equation for this. So the SPE is equal to 1/2 mv squared. So we know, 1/2 K delta X squared. So that's 4 joules. So let's plug in, I should plug that in for that part, I'll just rewrite it. 1/2, the spring constant is 400 Newton meters. I'll probably just leave out the units just to quickly get an answer. You're not showing your work, remember, for the final, equals 4 joules. So we're going to multiply both sides by 2 to get rid of the half, right? We get 8, but we're dividing by 400. So your displacement squared is going to be 4, what did I say, 800? I don't know what I just said. So it's going to be 8 divided by 400, whatever that is. And again, I'll just worry about the units. So again, I won't find my calculator. I'll just look for where I got it here. You're going to have to take the square root, right, of both sides. So delta X equals square root of 8 400ths. And that ends up, where's the answer? 0.14. And we need to slap a unit on here. So what do you think? Are we using SI units everywhere? Newtons, meters, yeah, joules. So let's call that a meter. I probably won't, well, maybe I will, I won't say that. I mean, I could ask you something about SPE just in terms of SPE, but the reason why I said to know that equation for SPE is because it might come into handy for these problems that are coming up in the next column. Okay, ignore air resistance for this one. We assume mechanical energy, that's ME, mechanical energy is conserved. In other words, for parts A through D. So just a little reminder is mechanical energy is just the sum of KE and all potential energies. Okay, so it does not include heat. That's the main thing that we're not including here. So mechanical energy, if the system is left alone to its own devices, will be conserved if there is no friction, no air resistance. It's just you only are having some kinetic energy turning into potential energies turning into kinetic energies, potential energies changing into each other. So the KE and the potential energies can transform into each other, but as long as there's no heat created, we would say mechanical energy is conserved. Does that make sense? Now, as far as the potential energies we have and we've been dealing with, we can say that mechanical energy would be the sum of, at any point, is the kinetic energy plus the GPE plus the SPE. And I think that's all we did for these problems. We didn't do any other kind of potential energy. So if there were no spring, then basically, which often happens, it's just like the K equals the GPE plus the KE. But let's go ahead and solve the problem. I hope you kind of get, again, what mechanical energy is. So back to the problem, it says, we assume it's conserved. You toss a rock straight up, so it leaves your hands with 40 joules of KE. At that height it leaves your hand, the rock has 8 joules of GPE. So I guess we're calling the ground R0 of GPE. So when it's leaving your hand, it already has some GPE. How much mechanical energy does it have when leaving your hand? Well, I hope you understood what I just said. 48 joules. It's the sum of the kinetic energy and any potential energy it has. And there's no springiness here, so it's just the Ke plus the GPE. How much mechanical energy will it have at its apex? Well, again, there's no air resistance. I'm implying, and I even told you parenthetically that somewhere that it's we're assuming mechanical energy is conserved. So when it reaches its highest point, it'll still have 48 joules of mechanical energy. At its apex, how much GPE does the rock have? This might catch you off guard a little bit. We haven't practiced this. But at its apex, how much Ke does it have? Well, what's the velocity when the ball reaches its highest points, or the rock? 0. So if the Ke is 0, but the mechanical energy is 48 joules, well, the only other mechanical energy besides Ke is going to be GPE. So that must mean that the GPE at its highest point is 48 joules. So all that original Ke, those 40 joules of Ke that it had originally, turned into 40 joules of GPE that were added to the original 8 joules of GPE. So we have 48 joules of GPE at the apex. The rock comes back down, still no air resistance. How much Ke will it have just as it reaches the ground? Again, we take those 48 joules and we just have energies interconverting into each other. So it's still no heat created. Just when it's about to hit the ground, the Ke would equal 48 joules. So you can see here, it's just 48 all the time. It's just turning into different forms along the way. Now, part E, we're going to get to a point where heat's created. And so now mechanical energy is not conserved. The rock hits the ground and comes to a stop. So now mechanical energy is not conserved. How much mechanical energy is at this point? Well, mechanical energy is the sum of the kinetic energy and the potential energies. Is it moving? No, it stopped, so no Ke. Does it have GPE? No, it's on the ground. And there's no SPE, so the mechanical energy actually is 0 at this point. So that energy had to go somewhere. So there is a more overarching conservation of total energy that exists that includes things like heat and sound energy and light energy and all those other things. So for the first process, all that mechanical energy was 48 joules. That was the total energy that we had all the time. So there still must be 48 joules somewhere at the end. It's just not in the form of mechanical energy anymore because we don't have any kinetic energy and we don't have any potential energies. So we must have created 48 joules of some other kind of energy that's not mechanical energy. And that must be thermal energy, in other words, heat. When it hit the ground, it warmed up the rock, it warmed up the ground a little bit. And sound energy, because sound energy carries away some energy. So that's kind of like a little, again, a primer about mechanical energy. Now, this is like a nice, easy problem, the kind where we fill in the blanks, where mechanical energy is conserved. So again, I'm saying we're assuming nothing that's creating heat. So mechanical energy is conserved. Don't worry about that term, conservative forces. Conservative forces are forces acting on an object that's not creating heat. It's just turning into some kind of potential energy. The rock is already coming down, as you can see with my motion lines, towards a spring. The spring, there's no... Well, I won't give this away yet. Then it comes down towards the spring. At time 2, the spring reaches its most compressed state. So that's time 2 over there. Before it springs back up. Fill in all the blanks. Okay. So SPE at time 1, do I see any spring compressed or stretched? No. So that's 0, right? So the mechanical energy, again, is the sum of the kinetic energy and potential energies, which is 9 joules. So jumping to time 2, what must be the mechanical energy at time 2 if, as I said, mechanical energy is conserved because don't have any air resistance or friction or anything? It also must be 9 joules. Now there is some SPE because we've compressed the spring, but again, this is that idea that comes up a lot with conservation of energy problems. If the rock has compressed the spring and we said it's at its most compressed state Before the spring unloads and shoots the rock back upwards, what's the velocity of the rock right then when it's most compressed before it springs back up? The velocity is 0. So what's the KE at that most compressed state? 0. But since the mechanical energy has to be conserved, because again, we're assuming no heat's created, what must be the SPE at this point? 7 joules. Hopefully that comes back to you, that you remember, oh yeah, that's right, that's how that works. But to make it a little bit more interesting, redoing the problem to make it more realistic, let's say now that the collision is going to create some heat, because after all, they're slamming into each other, and that's going to cause the molecules, atoms, to vibrate in those materials, which is increasing its temperature, increasing its thermal energy. Thus, ME is not conserved here. Remember that the total energy, which includes any heat or sound energy or whatever, is always conserved. Mechanical energy isn't, but total energy will. Fill in the blanks. Okay. So in time 1, we still have some kinetic energy. It's still above the ground, so it still has GPE. There's still no SPE yet. We haven't compressed the spring. So what is the mechanical energy? It's 9 joules. Now, has any heat been created yet? No, it's not until we get to collision. So what's the total energy here at time 1? 9 joules. Okay. So nothing's different than the first one because even though I'm saying heat will be generated when the rock slams into the spring, it hasn't happened yet. So I still have 9 joules of mechanical energy and total energy. Those aren't separate energies. It's just that the total energy is the same as the mechanical energy here. So let's get to time 2. I told you that in the collision, 3 joules of heat are created. Now again, this is where the rock or the spring is its most compressed state. So its velocity is 0 temporarily before it springs back up. So the kinetic energy is 0. Now we seem to be stuck here. What's the SPE? Well, what property or what energy is definitely conserved here on the 9 joules of total energy? Because the mechanical energy won't be conserved here because we have this non-conservative force. We have this heat being generated. So the mechanical energy is going to be the sum of the GPE and the KE and the SPE. But 3 of those 9, I'm going to point over here, 3 of those 9 joules are the heat. So how much is left over for mechanical energy? You can think of the total energy as, well, I don't want to say it's this, but I was going to say the mechanical energy, at least for this problem, is going to be the sum of the, I said that wrong. You can think of the total energy as the sum of mechanical energy and heat. Although again, there could be other energies like sound energy or light energy. But for this problem, that total energy is going to be the sum of the heats generated plus the leftover mechanical energy. So the mechanical energy must be 6 joules because 3 joules of that total energy and the original mechanical energy turned into heat. So now we can finish the problem. If the mechanical energy is 6 joules, which are these 3 things together, how big is the SPE? Yep, 4 joules. Okay, that's kind of longer than I expected to explain it. Sorry about that, but you get the idea. All right, here's a problem that I'm going to put, not this exact problem, but you're going to need to do a conservation of energy problem. And the whole idea here is we're not going to write like more generalized equations. The whole idea is before and after the energy is conserved. Now, as long as I'm doing no heat generated, no sound energy, whatever, if all that's happening is we have KE and SPE and GPE, it's just that they're turning into each other. The mechanical energy is conserved. So the total mechanical energy at time 1 has to equal the total mechanical energy at time 2. And yes, for the final, I'm not going to do something where mechanical energy is not conserved. I'll stay away from like heat being generated. And so you just have to know that it's changing from KE to SPE. Anyways, and GPE. So those 3 things are just changing among each other. So let's look at the problem, and I'll remind you how to do this. A spring with a spring constant of 100 Newton meters is compressed by 0.2 meters while a 0.1 kilogram ball is pressed against it. Then it's released. The ball is released and goes up a hill. At time 2, the ball has 1 joule of KE. So you see there's little motion lines. It's still moving. We want to know the height of the ball. at that time, and assume no heat's created. Unrealistic, but okay. Um, and therefore, the mechanical energy is conserved. So first, a couple of quick questions. What form or forms of energy are at time 1? Because you need to know this. So the spring is compressed. We have SPE, right? Is there any KE yet? No, because it's not moving. Is there any GPE yet? Well, it depends on what you define as your zero of GP, but why would we call it anything else than that being our zero? So it's not supposed to be, I don't get confused. I'm not saying one is up higher in the sky. I'm just showing a diagram at time 1 and time 2. So no, we'll say there's no GP. Why would we want to do that? We're not going to be able to solve the problem. So we'll just call where the spring is our zero of GP. Okay, what form or forms of energy are at time 2? Well, the ball is still moving, so it has KE. Now it's above what we defined as our zero of GPE, so it has GPE. But is there SPE? No, because the spring has now gone back to its relaxed position. So why do we need to do that? Because here in part C, we're going to set up our conservation of energy equation. And all we're going to do is write the formulas for each one of these energies at time 1 and time 2, unless I just give you the energy. Why bother writing a formula if I'm just going to give you the energy directly? So what kind of energy does it have at time 1? SPE, right? That's all it has. Now, did I give you the actual SPE in the problem? No, so we're going to have to calculate it. So the formula for SPE is 1/2 K delta X squared. That's the only energy it has time 1. That's all the mechanical energy at time 1. Now, it's going to equal the KE plus the GPE at time 2. Did I give you the value of the KE? Yeah, I actually did. I told you it was 1 joule. So why bother writing 1/2 mv squared? We don't know what the V is, so I'm just going to write KE. I'll write KE2, but there is no other KE to confuse it with, so you could have just wrote KE. And it also has GPE. Did I give you the GP at time 2? No, in fact, we're kind of solving for it, right? We're actually going to be solving for H, but you get the H from the GPE. So we're going to write MGH. And I probably on the answer here I put MGH2, but again, there's no other height to confuse it with. So that's what you do for these problems. That's the key part here. Well, actually, yeah, the key part. Sort of a key part is making sure you know what energies it has at time 1 and time 2. But then you set up your conservation of energy equation, where on the left, you put the energies of everything it has at time 1, and at the right, you put all the energies it has at time 2. And the little subtlety here is, yeah, if I just give you outright what the energy is, don't write the formula for that energy. We don't need it. But if I don't give you how much energy it has, and we're going to have to calculate it, put in the formulas for that. That's why I put formulas in for those. Now we plug in numbers with units. Again, you don't have to show your work. Then get rid of the units and solve. I just do that because I always want you to check that all the units look reasonable. So of course on the final, kind of don't waste your time. So 1/2, the spring constant is 100 newtons per meter. The displacement is 0.2 meters squared, right? Then KE is 1 joule. Great, we don't have to use 1/2 mv squared. The M is, I wrote that somewhere, 0.1 kilograms. We're on Earth, and we're solving for height. So notice we have everything except for H. Now, do all the units look okay? Am I using SI everywhere? Do I got newtons, meters, kilograms, seconds? Okay, so I'm probably pretty good. So let's go ahead and simplify this, and it'll look much friendlier once I get rid of that. In fact, I'll solve that thing on the left a little bit. I think I just solved something that looked like this. But anyways, 0.2 squared is 0.04 times 100 is 4 times 1/2 is 2. So that side's 2, right? Then we have 1 dropping the units. And that side is going to be 10 times 0.1 is 1, or H. Okay. I'm sometimes way too nice to you guys with these convenient numbers. So we move, I hope you can solve this, move the 1 to the other side, and we get H equals 1. And what do you think the unit is? 1 meter. Okay. So that's not an easy problem. I think you got good at them, but again, it's been like 6 months since you've done those, maybe 5. So just remind yourself. Okay, let's say we get a problem where we do a conservation of energy statement there, and we get this. So it has some GP at time 1, it has some KE at time 1, and it has GP at time 2. Well, we could plug in every mass and little g and h and v and stuff and solve for whatever we're solving for. But to make it go a little quicker, you see something we could cancel? Yeah, the masses. So if you get something like this, not that you have to, go ahead and plug in the masses, but why not just get rid of all the m's, and you can get gh1 plus 1/2 v1 squared equals gh2. That's not 2, that's squared, 2. And then you just plug in things. It's a little bit quicker. That said, sometimes you will have to do that, because I could totally give you a problem where I don't even give you the mass of whatever this object is. So if it's a ball or whatever, and then you'd be stuck. You'd go, wait a minute, he didn't give me the mass. How am I going to solve this? Well, then you have to realize, oh, wait a minute, I don't need the mass. They cancel anyways. You could even make up a mass. You can say, I'll pretend like it's 1 kilogram and plug in 1 kilogram if you want. But it's just better that if you can cancel something, cancel it. Now, I didn't do a problem like that. I don't know if I am later. I think actually 25, I'm going to do something like that, I think. Sorry, making you dizzy. I do feel a little guilty about, on the original little final hints and important information about finals, I didn't have this written, this SP equals 1/2 K delta X squared, because I think last year I didn't have time to get to spring potential energy. So I might just, for my conservation of energy problem, just give you this. But still, be ready for that just in case I decide to be mean. All right, a snow tubing girl pushes off at the top of the hill, so she is already moving with 5,000 joules of KE when she is 8 meters high. The 2+ girl have a combined mass of 60 kilograms. Assume there's no friction or air resistance, so mechanical energy is conserved. Again, mechanical energy is just the KE and any kind of potential energies, and it will be conserved as long as we're not creating some other form of energy that's not conserved, like heat and sound energy that's dissipating away from your system. Okay, find her velocity at the bottom of the hill. So right here, we're not worried about what's going to happen here yet. Forget about that. We're kind of ignoring that right now, okay? Let me get rid of that for later. But yeah, we just want to know at the bottom of the hill where she's about to go off some information. We want to find her velocity. So we need to do these conservation of energy steps. Now I said here, show the 2 steps. No, for the final, you don't have to. What I meant by the 2 steps is that, okay, plug in, write your conservation of energy statement, and then plug in numbers with units before you get rid of units, and then solve it. Okay, that was my only requirements for conservation of energy. Is write your equation in terms of the variables. Don't put in the numbers yet, of course. Then put in the numbers with the units, and then you could just simplify it and solve. Okay, so we're going to consider this. This is kind of important. Since don't worry about this yet. Who cares that she's falling off? We're going to call that my GP equals 0 there, okay? I know she's going to fall later, but we're just trying to find the velocity at that point. So why make it unsolvable by saying she has GPE there? Let's just say GPE is 0 there, okay? So let's identify what energy she has at time 1 and time 2. So at time 1, she already has some KE, right? We said she's already moving with KE, okay? What other kind of mechanical energy does she have? Does she have GPE? Yeah, she's above R0. She's 8 meters high. Does she have SPE? No, I don't see any springs or anything springy. So she just has KE and GP at time 1. Okay, what about time 2? At time 2, does she have GPE? No. Does she have SPE? No. Does she have KE? Yeah, she'll have even more KE. There's no friction here, so she'll have a lot of KE. So here's what you do, again, once you've identified, in fact, I'll write those down just to remind us. She has KE at time 1, she has GPE at time 1. Time 2, she has KE at time 2. And that's why I like to put 1s and 2s, because we don't want to confuse the two. So that's all the energies. So what we do, take your time when you do the test, make sure you don't make a mistake, is we're going to do our conservation of energy statements by summing the energy she has at time 1. If we're given the energy directly, we just write the symbol for that energy. If we're given information, but we're not given that energy explicitly, we're going to write the equation for that. So she has KE at time 1. Are we giving the KE? Are we given the KE? Yeah. So I'm just going to write KE at time 1. I'm not going to write 1/2 mv squared. I don't even know what the velocity is at time 1. She also has GPE. Am I given the GPE directly? No. I'm just told that she has some mass and some height. So I'm going to write MGH. And I'll go ahead and say MGH1, time 1. And at time 2, she only has KE. Am I given the KE at time 2? No. And in fact, I'm going to be solving for her velocity at time 2. So I probably want to write the equation, 1/2 mv2 squared, her velocity at time 2 squared. Does that make sense? That's the quote-unquote hard part there, is I'm hoping identifying the energy she has. And again, if I'm only going to do mechanical energies conserved, I'm not going to have a problem for conservation of energy where there's Q. So all you're looking for, very simply, is you're looking, does he or she or it have KE, GPE, and SPE? So if there are no springs, nothing springy, no ball, no spring, whatever, rubber band, it just comes down to, is there a KE and there's their GPE? And then you write your equation, and that might be the hardest part. And again, I hope you understand what I've been talking about. Why write 1/2 mv squared here when I can't even use it? I'm given the KE, so I'm just writing KE. And again, you don't have to show your work, but on your scratch paper, you probably are doing something like this to figure it out. But since I'm not given the GPE, I need to calculate it, so I'm putting MGH. And at the final, I could have written just KE2 and solve for KE2, but then I'm still going to have to solve for V. So since I'm not given the KE at time 2, I'm going to write its equation. So that's what I'm doing there. So let's go ahead and plug it in. I'm going to skip that middle step. We're going to trust that we have, I'm not going to try to trick you. I'm going to trust that I'm going to have all the SI units, and I'll just leave out the units. So KE at time 1 is 5,000. The total M is 60. 10 meters per second squared. Height 1 is 8 meters, and that's going to equal 1/2 the mass, which is 60 still, and velocity 2 squared. I could just leave off the 2 now. Now I'm not going to be confused with a V1. So maybe I'll do that just to make it a little simpler. Okay. Now, by the way, we weren't able to use that shortcut here, like I talked about here, because I didn't have the V at time 1. I had to write KE1. So yeah, I couldn't cancel M's, unfortunately, there. But it's not that hard. It's actually made it simpler. I just gave you the 5,000. That's better than having to put in the V squared and the 1/2. Okay, let's solve this. We got 5,000 plus 600 times 8, 4,800. And then we have 30 V squared. So this becomes 9,800 equals 30 V squared, or V squared equals 9,800 divided by 30, which is equal, again, I'm just going to look at my answer key. That equals 327, but realize that we just solved for V squared. So maybe on the choices for multiple choice, I'll write 327, and you might circle it. So we need to take the square root, and when you do that, you get 18.1. And then what do you think the unit should be if we've been using SI units everywhere? Meters per second. And again, I'm just going to give you SI units for conservation of energy. I'm not going to bother with foot-pounds and stuff like that and feet per second. Okay, now she goes flying off the cliff. So now she's going to do this. She's going to land somewhere over here. And we want to know what this distance will be. What's that distance? Okay. So this goes back to the previous unit where I said the horizontal velocity and vertical velocity are independent of each other. We know at this point, her velocity when she takes off is completely horizontal. So this velocity we just found represents how fast she's moving horizontally when she takes off. As long as there are no horizontal forces acting on her, she will maintain that 18.1 meter per second velocity until she hits the ground horizontally. So we don't need to take into account any kind of acceleration she's experiencing falling down. All we need to do is to find her displacement horizontally, is multiply her average velocity times how long she'll be in the air before she hits the ground. Again, who cares that she's accelerating downwards? All we want to know is her horizontal displacement. And if we know her constant horizontal velocity, that's all we need. Now, again, I mentioned this in the last review sheet, that a lot of people will say, okay, I need the V average here. And they go, she starts out, is that 18.1, but maybe she started out at 0, or she ends at 0 when she hits the ground, and they divide by 2 and they get 9.05. No, that's her velocity the entire time when she's flying. So her velocity is 18.1 meters per second as she's flying through the air. And I said she's going to have 0.5 seconds until she hits the ground. So she will be going a distance of 9.05 meters. Okay. Number 26, we're getting close to the end. These last ones, I'll maybe take a little explanation, but mostly they're going to be just plugging things into equations. The simplest way to write the SI in imperial units of power are the watt and the foot-pound per second. Write the watt 3 other ways. Yes, there are 4 total ways to write power in SI units. And the foot-pound per second 1 other way. So the watt, it's a unit of power. It's how the energy changes per time, which I'll get to in a minute. And so the watt is equivalent to a joule per second. How many joules are consumed per second, how many joules of work you're doing per second, that type of thing. But a joule is a Newton meter, right? So we could write it as a Newton meter per second. But any of those, I just want to explain it, but you can also get kilogram meter squared per seconds cubed. And you can kind of see that from that one, that a joule is a kilogram meter squared per second squared, but then we're dividing by an additional second. Really complicated looking units, which is why we just typically write watts. Then the foot-pound per second is the units of power for the imperial units. And so writing it one other way, well, a foot-pound is a slug foot squared per second squared, and we're dividing by a second. So the one other way that we'd write this is a slug foot squared per second cubed. Okay, again, write those down on your review sheet, or cheat sheet, so that if I do ask a question like that, you are ready for it. A car driving down the street has an initial KE of 50,000 foot-pounds, and it accelerates to get onto the freeway, achieving a new KE of 215,000 foot-pounds in 1.5 seconds. What power did the car use, if that's the right word to use for it? So these, I won't write them, I'll just point at them. Just as I said, there are 2 ways of thinking about impulse. Impulse J is the change in momentum, delta P, which is also equal to the force times the time. And I said that work is the force times the distance, which is also equal to the change in energy. Power, there are 2 ways you need to think about it. And depending on the context of the question, you, again, be flexible and be able to use either way. So power you can think of as not watts, don't get confused. That's not the units, that's the symbol. That's the work you do divided by the time that you do the work. So that's gets a little confusing, but that's not watts, that's work. But it also represents the change in energy of the object divided by time. So depending on, again, what's asked in the question, you've got to be able to use both ways. So what power did the car use? Is there anything there? Well, I guess it's almost equivalent, but I'll explain it 2 ways. You can see how it can be explained with this equation and with that equation. I would look at this and say, well, assuming that that's the total energy of the car, I'm not going to worry that it's going up a hill. I didn't say it clearly enough. I didn't say assume it's on a flat surface or whatever. It went from having 50,000 of energy to 215,000 of energy. So how much did the energy change by? 165,000, right? So it changed energy by 165,000 foot-pounds. You see that? And the power is the change in energy over time. So if it changed 165,000 foot-pounds in 1.5 seconds, we divide those, and that's going to give us the power in foot-pounds per second. And again, just relying on my answer key to be right, so I don't have to put it in my calculator, that is 110,000 foot-pounds per second, which is the proper unit for imperial power. Now, I kind of chuckled a while ago because I said I was going to treat it like I'm doing two different problems, but you can think about it in terms of this equation. Remember that when you do work, you change the energy, right? So I could ask you, well, how much work was done by, I guess, the engine to increase its KE? Well, it did 165,000 foot-pounds of work, right? Because it changed its energy by that much. So it's the same problem, basically. It's whether you're just thinking kind of, how much did the energy change by? Or you're thinking, well, how much work was done on it? How many horsepowers is that? I probably won't ask this, but you should write it down. So it'd just be converting, and maybe just as a reminder for conversion, a little extra practice, we have 110,000 foot-pounds per second. And remember the conversion factor, we're trying to get to horsepower, where that's the conversion factor. And we just need to put the appropriate one on the bottom to cancel. So it doesn't look like it. I know we have a numerator and denominator here, but we need to get rid of foot-pounds per second. So I'm going to put 550 foot-pounds per second on the bottom and horsepower on the top. So the foot-pounds per second cancel, and I'm left with horsepower. And that turns out to be conveniently 220 horsepower. And then practicing a little bit of kinetic energy and just kind of realizing how we can manipulate these numbers to solve for other things. If the car has a mass of 100 slugs, which is a reasonable mass for a car, what was its initial velocity? So remember, we said that the KE at the beginning was 50,000 foot-pounds. And we know that KE equals 1/2 mv squared. And we want to know its V, right? And again, if you're not great at algebra, that's okay. Again, you'll be fantastic soon. Is write down the other versions solved for other properties. So V, you would find out, is equal to 2KE over M, all square rooted. So if you don't think you could get that, write it down. So if you're doing a problem where you have the KE and you want to know V, you could just look at your cheat sheet and use that. So we would put in, I want to do all this, we would just show you what I'm plugging in, 110,000 foot-pounds. And then we're going to divide by the mass, which is 100 slugs. And again, I won't go through it, but we're going to, battery's running low, but we're almost done. It's going to cancel. Remember to square root. And just look at my answer key. We get 31.6. Now, what's the unit? We want to slap on a unit here. Should I put meters per second? No, we're using imperial units. So the official imperial unit for speed and velocity is foot per second. All right. Number 28, you lift a 2.5 kilogram brick at a constant velocity from the ground to 2 meters high. How much work did you do on the brick? Okay, we can think about this two ways. First of all, let's think about it in terms of work equals force times distance. So what force do we have to exert on the brick just to lift it at constant velocities? We're not speeding it up, we're just lifting it up to higher. Well, you need to exert a force equal to the weight of the brick. So whatever the weight of the brick is, that's the force you have to exert to move it up at constant velocity. But as I said in my hint, I won't give you a hint on the final, is that the weight of the brick is not 2.5 kilograms. We need to find the weight. So I'm writing small so that I have room to do this another way. The weight is the mass times the acceleration due to gravity. So 2.5 kilograms times 10 meters per second squared equals 25 newtons. So now that we know the weight of the brick is 25 newtons, what force needs to be exerted? 25 newtons. And what distance are we exerting the force? 2 meters. So the work we're doing is 25 newtons for a distance of 2 meters. We're doing 50 newton meters or joules of work. That's how much work we did. Now I'll go ahead and solve this, but I'll go back and think about part A a different way. So the power, remember, is the change in energy over time or the work you do over time. So if I did 50 joules of work in 0.5 seconds, don't think that is, I forgot, some people do weird things that I'm not sure, but that's 50 times 2, because it's 50 divided by 1/2. So that's 100 joules per second, which is a watt, right? So that's the other way of, I don't need to box that. That's not the answer, but I'm just kind of pointing out that that's the same thing as a watt. Okay, the other way you could do A is you can think of it in terms of work equals the change in energy. So all we need to do is figure out what the difference in energy it is. So if the block is on the ground initially, its GPE at time 1 is 0, right? So if we want to know how much GPE the block has 2 meters high, we just need to use the GPE equation at time 2 and say we take the mass times the acceleration due to gravity times the height, which is 2 meters, and you figure out, unsurprisingly, that the brick has 50 joules of GPE at time 2. So again, if you think of work, if that's what first comes to your mind, that work is equal to change in energy, you just have to realize, okay, what's the energy at time 1? What's the energy at time 2? And you think to yourself, well, it's on the ground at time 1, 0, and its energy at time 2 is its GPE, 2 meters high, that's 50 joules, and you get that the work you're doing is 50 joules. And then you do part B the same. Okay, a few more questions. I got to do this before the battery's dead. How much energy does a 25 watt bulb use if you leave it on all night from 9 p.m. to 6 a.m.? So a reminder, again, you'll have these written down, that the power is the energy that is changing. In this case, we're using energy, we're consuming energy, divided by the time. So be flexible, be able to solve for different things. So we're looking for how much energy does it use? What's the energy consumption? So the energy consumption, the change in energy, how much you're using, if you solve that, whoops, don't mean to do that, is the power times the time. So the power is 25 watts, which is the same thing as a joule per second. That will help you understand what we're going to be doing here. To figure out how much energy, how many joules you're using, you need to multiply this by time in seconds. So 9 p.m. to 6 a.m., that's 9 hours. So you would need to convert the 9 hours to seconds. And just to save time, I looked at my answer key. I can't do that in my head. 32,400 seconds. And so we multiply it, seconds cancel, and that ends up, drum roll, to be 810,000 joules. So there'll probably be like one problem involving power like this, some variation of the problem where you're using P equals delta E over T, or P equals WT, or something like this where you're solving for maybe time or energy. All right, similar question number 30. If a light bulb uses 60 watts, 60 joules per second, how long until it's used 120 joules of energy? So it's just the same problem, but solving for a time now. So maybe just piggybacking on that one, solving for time, time is going to be the change in energy over the power. And again, if you don't think you can solve for this, write it on your cheat sheet. So the change in energy is 120,000. I know it's energy because I told you of energy, plus it's in joules, which is the energy unit. And the power, if I put 60 watts there, it might be kind of confusing how these things cancel and what your unit would be. So I think I'm going to prefer to write a watt as a joule per second. So that means the joules cancel. We have 1 over seconds in the denominator, but that flips to the top when I divide. So that ends up getting you 2,000 seconds. Okay. And the last one. A motor with 80 foot-pounds per second of power lifts up a 40-pound crate. If it lifts for 3 seconds, how much work will the motor do on the crate? Again, just manipulating the power equation, but this time I'll use, instead of power equals delta E over T, power equals the work you do over time. Again, that's not watts, that's work. So we're looking for how much work. What do you think we're solving for? W. So you get W equals PT. Again, if you don't think you can solve that, write it down. So anytime you kind of identify what things are, there's my P, there is, well, I won't talk about what that is yet, but there's my T, and it's looking for W. So it's kind of giving me a clue that I'm using, that power equals work over time. I'm using that equation, but I'm solving for work. So the power, we know, is 80 foot-pounds per second, and we know the time is 3 seconds. So we're going to put in 80 foot-pounds per second. The time is 3 seconds. So seconds cancel, and we're left with 240 foot-pounds of work. Okay. Since the crate is 40 pounds, That's the weight. In other words, that's the force we need to exert, right? The motor needs to exert a force of 40 pounds if we're lifting it at constant velocity. We're not accelerating it. We're not giving it KE. Using the work you calculated from the previous question, how high will the crate be after those 3 seconds? So going back to work now, the other way we think about work besides force time, besides change in energy, is force times distance. So we're saying how high will it be compared to where it started? We're looking for distance. That's equal to the work you do divided by the force that's being applied to it. So again, if the object is 40 pounds and we're just lifting it at constant velocity, we must be exerting a force of 40 pounds. So we're doing 240 foot-pounds of work on it. And the force we're exerting is 40 pounds, so the pounds cancel. And when you divide, you get 6 feet. So it'll be 6 feet higher. Okay, sorry, that probably took a while. It's probably over an hour. But I just wanted to stop and kind of explain things. A lot of work, right? But again, maybe this year, I don't have time to ask a lot of questions. So I'm guessing there'd be 13 questions or so on the final involving this material here. So don't kind of panic like, oh my God, I can't do all that. You won't. There were 31 questions here. So it'll be okay. But just make sure you understand all those concepts. Okay, see you guys soon.